Hey, welcome back. So this session will have two discussions. One on observations led by Stefan Kraus, and the second on populations by Maxwell Moe. And so, Stefan, you can take it away.
Okay, yes. Well, thanks. Welcome back to the last session of the day. I'm Stefan, and I would like to lead this discussion on observations, with a focus on binary formation and disks. And I think already several talks this morning and afternoon made the case that we can link the binaries with, on the one hand, planar formation in the low mass regime and then the supermassive black holes. But as an observer, I just feel very fortunate that for the disks around stellar mass binaries, we can see all this details with spatially resolved observations nowadays, constraining you, for instance, the global disk properties, allowing you to see substructures in the disk, getting physical parameters such as temperatures or dust compositions out of it, even 3D velocity fields of showing warps in the kinematical structure, for instance, or the three-dimensional structure, and then being actually able to see the bodies that produce all these structures, namely the binaries. And so I think there's a very nice opportunity there to make use of all the information that we have here. And so we want to discuss about that. And some kind of an overarching theme was also that we have multiple theories of binary formation, for instance, cloud fragmentation and disk fragmentation, both supported by observations, as we see here, for instance. And somehow we now need to migrate these binaries to the separations where they're actually observed, including also very close systems. So there's certainly also some aspect of orbital evolution that we need to constrain with observations. And so I thought maybe a good way of structuring the discussion section is to think about it in terms of very early evolution, basically what John Tobin talked about, fragmentation in clouds and class 0 sources, then later observations on pre-main sequence binaries and disks, and then maybe also what we can infer from observations on main sequence binaries about this orbital evolution and formation processes. So to kick things off, I just brought here up one question about the class 0 sources that John talked about. So do we think that these binaries that we see there are really representative for the initial binary population, or has there already been some evolution happening already at that stage? What are your opinions on that? Is John still there in the online audience?
Yes, I'm here.
Okay, so what is your take on it?
I suppose my take on it is that I think it's the closest thing we're going to get to an initial binary population. I think there's a couple of things that sort of point to it being at least a pretty good representation of it. One of them was in one of my final slides, I showed the multiplicity fraction and companion fraction between 100 and 1,000 AU for each class. And what you could see was that no matter what your YSO density was, the class zeros had the same multiplicity fraction and companion fraction between 100 and 1,000 AU. So I think that to me, that suggests that there's probably been little evolution for class zeros. I think if you get to class ones and flat spectrum protostars, I think their evolution is sort of mixing in with initial conditions, but I think class zeros are as close as we'll get, even though they may be imperfect themselves.
Okay,
I'm just gonna, for the black hole folks in the audience, do people not know what class 0 is well? People confused. Okay, class 0 is the youngest objects deeply embedded. It is based on an infrared SED classification from the early 90s, but think the first 100,000 or a couple 100,000 years. Class 1 is the next phase up to maybe a mega year, where the mass is probably not so much on the large scales, but in the disk itself. And then flat spectrum is like, or T-Tauri. Those are things where most of the action has happened. The star has accreted most of the mass that it's going to have had, but probably it has not yet arrived on the main sequence. So that is what class 0, class 1, and class 2 mean when star formation people talk about it. Okay.
I think Nathan had a question or comment online.
Yeah, I just want to suggest one argument you can make, which is maybe not as strong as you would like to be able to really constrain like the underlying initial distributions of the binary populations, is simply things that like if you think about the parameter space in sort of the binary fraction, higher multiplicity fraction plane, if you start with very, very low binary fractions and very, very low multiplicity fractions, there's no real way to you're too hot in an environment usually, and there's no real way to make up a whole bunch of, for example, higher order multiple systems. So there are regions of parameter space that, based on current day observations, I think you can rule out at least, even though it still leaves a lot of degeneracies and a lot of parameter space that would still need to be constrained at.
Can I just jump in with another clarification for the non-stellar people in the audience? There's a few terms that have been thrown around, including binary fraction, multiplicity fraction, and companion fraction. Binary frequency or fraction means what fraction of the stars are in binaries. Multiplicity usually includes higher order multiples. And if you hear somebody say companion fraction, that means on average, how many companion stars does a star of a given mass have? So for sun-like stars where things are typically in binaries or singles and triples are a little bit less common, those two numbers often are the same. If you're talking about O stars, the companion fraction is often greater than 1, meaning that on average, the typical O star has at least 2 companions. Are there any other terminology questions that the black hole people would like us to clarify so that we can be speaking the same language, which is a goal of this conference?
Mm-hmm.
I think it still kind of fits in the terminology, not a black hole angle, but class 0-1 is still relatively low mass stars. And I wanted to clarify, if we go to more massive objects, what names are we talking about, or would they be included in these classes?
Right, as early as you can get. So, I think we have a class 0 for high mass protostars as well.
Yeah. And then after class 0, they're like gonna explode. So that's kind of
exactly. Okay. So after we have our initial populations of what is happening with these companions after they are interacting some with the disk, and here I wanted to maybe follow up with the questions that we raised already on Friday, namely whether we can maybe make use of these handful of very well constrained systems where we have information about the disks, where we have the orbits, where we have the global disk parameters, and can then do hydrodynamic modeling in order to benchmark our codes and get fundamental parameters constrained in these poster child systems. So I wanted to continue that. What do you think are the challenges, for instance, to do such detailed modeling of individual systems, and maybe what other information would you need to set up such models?
I mean, as I tried to say at the end of my talk this morning, I think modeling specific systems is absolutely fantastic. But it's still very difficult. I mean, it's very time consuming, and the the fewer parameters you have, obviously, the more time consuming it is. And, you know, modeling GWRE with you, I realized that even if you have very well constrained stellar orbits and quite well constrained disk parameters, there's still a lot of parameters you don't know very well. And for these complicated systems, getting detailed agreement is almost impossible. So, you know, in the early days, I sort of thought, you know, wow, we'll be able to measure disk viscosity directly by comparing numerical simulations to observations. And that might still be possible, but it's, I think, a lot harder than I'd anticipated just because of the things that you don't know. I mean, for example, disk surface density profiles. I mean, observers just can't measure that, basically, right? I mean, you measure CO in disks, but it's probably CO at the surface of the disk, and you don't know what's happening with the bulk of the gas and so on. So there are things where you're going to have a very hard job getting detailed parameters. So I think we can definitely study things like, you know, cavity creation and spiral arms and disk breaking, ideally, and things like that. But there's always going to be some element of we'll get something similar, but not exactly right, I think.
Mm-hmm. Yes.
Well, maybe I mentioned, I think might be another problem, but maybe also a question, which is everything in the simulations is very time dependent. So if you have only one snapshot of one system, it's going to be very hard to compare to one snapshot of one simulation because this simulation keeps changing. I think I kind of started discussing this last week, but one helpful thing to this would be movies instead of pictures from observations. Is that possible?
Right.
Is that possible to in any approximation? I mean, are there systems small enough that they actually evolve in human timescales?
For the very inner regions, I think we might get to that point soon. But was there another question or comment?
Daryl, did you have a question?
No, I was speculating. So I said, why did you say that?
So it's also about being smart, like what to compare with, right? Like you could still compare the characteristic scale of your structure, or basically need to think beforehand what is kind of a fundamental quantities that you can compare, even if the structure is changing. Was there another idea on that? Steve?
So is the answer to the movies it's possible?
Well, in the innermost AU, structures are changing fast enough, right? Like there is, if you make images over a few weeks or months, you will see things moving. But if you think of typical ALMA studies, there of course it takes years to see just a few degrees of motion. So in the near infrared regime, I think we can expect some progress on this soon with getting better and better imaging capabilities.
Yeah, I would be very interested in knowing whether John can determine anything about the morphology of the disks that he's seeing and whether they're in any way different than the disks that you see in the T-Tauri phase.
John Tobin, would you like to reply to that?
Yeah, so this is whether the protostellar disks are, I guess, overall similar to the T-Tauri disks. We've done a bit of, well, I think the answer to that sort of depends on your assumptions. So just using observational data, I mean, looking at distributions of disk masses and so forth, we find that the disks tend to be overall more massive by about a factor of 5 to an order of magnitude from the protostars to the T-Tauri or class 2 disks. So they have a lot more mass. But then as far as like radius goes, we looked at the distributions of disk radii, and the disks around protostars tended to be smaller than the disks around class two systems. Like, for instance, disks in Taurus tended to be quite a bit larger than the disks around protostars we were finding in Orion, which that could be due to viscous spreading. It could be due to initial conditions. I think we weren't quite certain about that. But then
Orion also has this issue with hot gas. It's a very hot region, right? Temperature-wise, the ambient temperatures are hot. So there's a lot of evaporation.
Yes, I think I didn't catch all of that, but I think if I caught the gist of it, you're saying that the temperatures tended to be warmer. Was that correct?
Yeah, I mean, Orion has a very hot background, right? There's a lot of disk evaporation in Orion.
Well, we're looking at sort of Orion as the molecular cloud system. So there are regions of Orion that aren't too unlike Taurus. I mean, where the populations are rather distributed and they do not have very strong UV. But you did say something that is more or less correct, which is the disks around protostars do tend to be warmer than the disks around class 2s, and that's because of the surrounding envelope. And then radiative transfer models indicate that you're going to have an overall warmer disk, such that your CO is going to be all evaporated through the midplane out to 100 or so AU for the protostars, but not for the class 2 disks. And that's due to the irradiation from the envelope.
Mm-hmm. We also expect that there should be potentially non-Keplerian flows in these class 0 objects, or in the case where they are more Keplerian, there'll be a lot of self-gravity playing a role. So there might be some differences arising from that in terms of, I guess you can't see spiral structure.
Well, yeah, I think there's a few cases of spiral structures, though the details of the kinematics haven't.
For instance, this is, I think, like a class 0 high mass case with spirals. Sorry, John.
Yeah, I was saying, I mean, there are a few examples of spirals for class 0s, though we haven't really done the analysis for how much of it is non-Keplerian at this point. For instance, I had the velocity field of L1448 in my talk, but if you subtract the Keplerian profile from that, I don't know exactly what the non-Keplerian portion looks like.
Okay. Ben, there's a question or contribution?
Hi. Yeah, this is, I guess, a callback to the previous discussion on can observers make movies, which is a great theorist question. Yeah, I think there is an opportunity to do things in time series, but it requires systems that you can't spatially resolve. So we're talking about measuring mass accretion rates onto stars. We're talking about trying to detect gas within the gap between the circumbinary disk and the inner binary, and we're talking about trying to look at changes in the structure of the disk, the inner parts of the disk, which you could, for a binary with a 10-day orbit, you could feasibly do from the ground. But these are all kind of spectroscopic tracers, and so I think that's kind of one missing link, is going from, okay, here's a model, here's what I can expect, like the emission lines from the disk or from the star to look like, either from the disk or from the accretion process itself. So I think that's kind of an interesting avenue that I hope we can continue to explore this weekend or this week. But I think that's it's a tall order.
Mm-hmm. Right.
Yeah,
okay.
so just to partly answer Zoltan's question, there are observations which people see the structure change, right? The shadow, several systems with the shadow on the outer disk, those shadow moves on years time scale. Although those shadows are seen at outer disk, but they are caused by the inner disk, which blocking the central star. So the time scale of the precession and everything is much shorter time scale. So that's why you see those shadows like TW Hydra, the shadows are moving like over years. So you do see things moving at a short period of time. But the issue is because those shadows are cast by the very inner disks, which is unresolved. So we don't know what's the size of the blocking inner disk, or whether it's due to some minute spherical accretion streams. So that is something we cannot model. But observationally, we do have like the movies, like disk processing or things.
Mm-hmm.
Could be compared to
mm-hmm. And was there another? And in this context, I wanted to kind of ask the theorist whether there's any predictions for phase-dependent behavior beyond kind of the preferred accretion onto secondary scenarios that we already talked about, and that seems to be well supported by observations in the meantime. So basically, most of the accretion goes onto the secondary in this unequal mass binaries, prevent sequence binaries. But can you think of other predictions that observers could test in the near future for time variability that is somehow linked to the binary parameters?
Dong, do you want to talk about phase-dependent accretion on binaries?
Okay.
The period depends on the eccentricity of the binary. But if you have a circular orbit, then I think many people have got this result. I don't know who got it first. The period is five. The dominant periodicity is 5 times orbital period of the binary. Whereas if you have eccentric binary, as long as it's slightly eccentric, like greater than 0.1, then the dominant variability becomes the orbital period. So that eccentric behavior was found by Diego Menuz, I think. And so I don't know whether this has been observed, this kind of behavior. Yeah.
Mm-hmm.
Ben, do you want to go ahead and do you want to comment on that, since I think you're being called out for having observed something like that?
Yeah, sure. Yeah, so we've observed pulsed accretion in eccentric binaries. So short period systems, less than 20 days, eccentricities of like 0.6, and we see bursts of accretion every orbital period at the periastron passage. So that seems to drive pretty well with the predictions from theory for the eccentric systems that were just being described. For one of those systems, we were able to measure the accretion rate onto both stars, and we actually found in one particular system, TWA3A, that the secondary was accreting more than the primary. Not like a lot more, but it was accreting more. I think that's interesting, and is maybe one of these was perhaps predicted by one of Diego Munoz's simulations that showed a precessing inner cavity that was eccentric, and so each star kind of takes turns feeding from the dominant side of the inner cavity. And as that precesses, the primary and secondary accretor alternates back and forth. I think on the long term, it equals out towards the secondary gets more, but in instantaneous slices or in individual orbits, the secondary can accrete more, or is predicted to accrete more, which is what maybe we were seeing in that particular system. There's only like 2 or 3 systems where that's been done. We're trying to find more to do that now. And the kind of deeper we go down into this hole, the messier it's getting. Turns out DQ tau and TWA3A are really excellent examples, and nothing else is seeming to kind of match up just as well. But maybe that's for another time.
Okay, thanks. Rajika?
Yeah, hi. Your question concerning theory, predictions of phase-dependent accretion. I don't know if this applies, but I was working with some observers recently who looked at a young protobinary and found this weird radial velocity structure. And I did some zoom-in simulations of binaries that I was looking at, and we found that for particular mass range and separation range of my binaries, so the binaries evolve through different separations, we found that we could reproduce this RV structure if the binary was, if we had high inclination angles and the binary had this typical separation. And that was very neat because we were finding that we got that at apastron. We got the RV structure at apastron on our simulated binaries. And I don't know if that's one way of using the theory to predict observations. It was opposite, obviously, but it would be neat to see if we could find this particular RV structure in other binaries. And but yeah, it was a bit hard because the binary that we're observing, we don't really know about the orbital parameters, but if we knew about other binaries and see if we could get this RV structure at apastron, that could be neat. But yeah, this is a very particular case of something other than looking at accretion and phase. This was another this was a different scenario where I was just looking at binaries and seeing what was happening with the gas around and finding that we could reproduce this structure at apastron. Sorry for rambling, it's 1 a.m. here. No. But yes, that could be one way to get other predictions that are not just phase-dependent accretion.
Okay, thank you.
So I apologize if this is asking a question that's been answered before, but I'm new to these observations. So I'm wondering if I can draw Ben back out again and ask, when you start to think about all these different components, are you modeling, or when you make the observations, can you see SEDs from each of the different components? Are you really looking at some sort of composite light curve that is then being fit to pull out the different components? Like, what do these observations actually look like from one observer to another?
Sure. Yeah, so I just put 2 links in the chat for what I'm referring to. So what we do is, for the mass accretion rates, we take U-band light curves, and you can measure the UV excess over the photosphere. And it's basically you just measure that variability, and that's a pretty straightforward measurement to make. You can see actually the DQ tau light curve from K2 is just like exquisite. You see sinusoidal spot modulation, and then boom, accretion bursts, and then repeat. It's really excellent. So that's how you can do time resolved mass accretion measurements. To actually measure which star is accreting, we're using accretion emission lines. So in particular, we were using a narrow accretion tracer. It's a helium-1 line in the optical. And ideally you could use something like H-alpha, but it's so messy that you can't really learn anything about the velocity structure of what's emitting where, because everything is so broad. This helium line is really narrow, and you can use it to isolate the velocity structure of each star. It helps that they go through a burst of accretion near periastron when the stars are widely separated in velocity space. And so you can spectrally decompose kind of the velocity structure of those emission lines to figure out where material is falling onto the stars. If you want to go into the disks, that's kind of more kind of Keplerian modeling and looking for asymmetries in kind of a classic double-horned profile that's kind of probing the inner part of the disk. And then the last thing is that you can actually, James Muserl has a paper on DQ tau where he sees dust come into the cavity, it heats up, then sublimates, so you have this brightening of the infrared color that then disappears, and then you have an accretion burst. So it all kind of hangs together in this nice stream-fed model. Hopefully that is explicit enough.
Yeah, can I just make it while I'm walking back? For those of you in the online world, if you want people in person to see your links, I suggest posting them on Slack because anyone not on Zoom right now will never see it.
I'm just wondering whether all of those observations or predominantly those observations are made in the UV. You said the U band was, and is the helium-1 line also a UV line? Am I remembering that right from like AMCVN systems, or can you observe it elsewhere?
This one is 5876 angstrom, so right in the optical.
So I have two quick questions also for Ben and maybe Dong, but one is, if I remember, the pulse did not actually coincide in this system at the periastron, whereas the theory predicted it should precede the periastron. So what did we learn from this offset? Did we learn something interesting physical from this offset? Number two question is, has anybody seen the 5 orbital modulation that we all think should be there from the lump?
I'm happy to field this one if that's okay. Yes. So the first question was, sorry, I forgot. It's been a long day. I'll go to the second one first. The circular. Okay, so the 5 period pulses in circular systems. The amplitude of the pulse in those circular systems is much lower than the amplitude in the eccentric systems. And so my feeling is that that hasn't been seen because the stochastic variability that happens constantly in these accreting systems is more than enough to wash out that kind of sawtooth rise that happens every 5 orbital periods. So I've tried to look for that in circular systems, but haven't found anything that looks like it has peaked out of what is just stochastic variability. So the first question was then, what did we learn about the timing of the bursts? I don't know. I think it's hard. The stars in our situation have magnetic fields around them. That magnetic field truncates the inner part of a circumstellar disk. And so these systems probably don't have circumstellar disks. Their magnetic fields truncate the inside and dynamics truncate the outside. So there's probably not a stable disk of material around either star. But that's what the models are predicting right now. So like the Munoz and Lai simulations that I refer to in my papers, they have circumstellar disks around each star, and then what actually gets the material onto the star are these torques as the stars go through periastron passage. That's not happening for ours. I think, something like ours is probably more similar to like the Artemis and Lubo simulations from 96, where material just falls out of the disk and onto the star directly, just because there's no buffer in the systems that we're actually observing. So that's a limitation to comparing our observations to kind of the really state-of-the-art models that are high resolution and resolve these small disks, is because they're not actually there in the systems that we observe.
Okay. Yes, I agree. The system that Ben was talking about, the star has the effective size because of magnetic truncation, has the effective size that has a significant fraction of the binary separation. So usually when we do simulation, we want to have a very small black hole, right? But there, for this system, it's actually very nice. It's very big, right? So as a result, that can in principle explain some of the phase shift that you're talking about.
I wanted to bring up maybe also another topic that I think has not been touched on so far, also in the last few weeks. That has been namely on the role of triggering maybe larger accretion outbursts and the link to multiplicity there. Like F-Orionis stars some of them are known to be multiples, and I think there were also papers, for instance, by Bo Rapert on that decaying higher order multiples could trigger such outbursts. So do you think that's something the field is moving towards too, or is that more related to disk instabilities? And what is the opinions on that aspect of time variability to get this really strong accretion outbursts?
For the black hole people, FU Orionis systems are young T-Tauri systems that experience like several order of magnitude changes in their luminosity with a rise time of order a decade and potentially lifetimes of up to 100 years. We have not yet seen one go outburst yet. Is that correct? One has just gone out of outburst. Okay, so most of them are still outbursting, but there's not that many of them known. And the statistics are that not 100% of them are known to be in binaries. Now you're all on the same page.
Max?
Yeah, so I'm working on this variability survey of the Triangulum galaxy, M33, and comparing current epochs with data taken 15 years ago, trying to find these FUers in this external galaxy. And the main reason we have to do it that way is you need a decent sample size. You find enough FUers. But the biggest thing that's been trying to get FUer rates, these outburst rates from galactic FUers, is knowing the denominator. What's your sample size of pre-main sequence systems you're looking at? And so looking at external galaxy over 10, 15 years, I think we might be able to measure the rates, and then we tell us about whether it's a single star phenomenon or you need binaries driving some kind of dynamical instability.
Right, that's something the LSST and Gaia will help a lot to push up statistics. And as observers, we also just tend to fit these systems as hierarchical systems, but is there maybe a chance of still finding systems that are not stable and could still decay? Like, what is the likelihood of finding subsystems? If we fit orbits such as GWRE, typically we just assume it's a stable hierarchical system, but I think that's not really tested in any observation cases. So whether this assumption is true.
My guess would be that those that are easy to demonstrate that they're unstable would have already become unstable. And those that are very close to the instability limit, then your observational uncertainties are going to make it unclear whether it's unstable or not. So that would be my guess.
We have a raised hand on Zoom.
Yes, please go ahead.
Hi again. So back to the FUR and stuff. A paper from Burchett et al., Daniel Price's group, they were very close to simulating an FURI outburst, and the way they did it was have the primary star with the massive disk and the secondary plow through it. And that was really convincing, and I guess it might suggest that FURI outbursts could be more catastrophic as opposed to evolutionary, and maybe we should look at what kind of environment FURIs occur in. Do they occur in high stellar density places, or can they occur in other places? And maybe this will give us some insight into what triggers the bursts if they are actually just catastrophic interactions as opposed to evolutionary from young multiples forming.
I think John wants to follow up on that.
Yeah, I was going to mention, at least some of these known FURIs are fairly isolated systems. I'm not familiar with all of them, but I mean, like FURI is in the Orion constellation, but I do not believe it's located in a particularly crowded area of Orion. And another one, which is V883 Ori, that one is quite isolated relative to its surroundings. So I think you find them both in clustered environments like HBC 722 and in fairly isolated environments.
Yeah,
okay.
So I follow John's comments. Some FURI are in binary, like FURI itself is binary, and recently the ZCMAC system are in binary, and these are double FURI system. But they are very far away separated. They are not very close binary. And there are also ones very isolated, like a V883 Ori with a beautiful AMA image, like 100 AU disks. There is no perturber close by. So it seems you have both.
On the other hand, for Z-Canis Majoris, I think they just found evidence for stellar flyby, which could have triggered.
Fiori is actually a triple too, wide triple.
Okay. We can touch in the last 5 minutes maybe on the third aspect, namely that, as was mentioned already, that Gaia data release 3 is coming up on the 13th of June. And so we're going to have a lot of new diagnostics there that we can compare to, like distributions of multiplicity and companion fractions that were already explained, but period and eccentricity. And here I just wanted to outline again that there's this degeneracy that was also mentioned, namely that you're going to measure the photocenter motion of the system, not the period and not the semi-major axis directly. But still, there should be plenty of distributions you can compare your population synthesis models to. So, for instance, we could discuss also the aspect of spin and spin orbit alignment. That should be possible to do for some of these Gaia systems. So, and so I thought it's an interesting topic of whether we might be able to separate processes that induce misalignments at the formation stage and then later in the orbital evolution, right? Like if you form a binary through cloud fragmentation far away, the spins will be randomly distributed, while in disk fragmentation you might expect them to be aligned. And so maybe spin-spin orbit alignment could be a good tracer for the formation process. And then if you have other dynamical interactions happening later on, this can tilt the orbit, but less likely the spin of the systems. So do the theorists agree with that kind of broad idea? But it's difficult to really change the spin of a star through things like Kosa-Lidov or orbital evolution.
Yeah, I was struck by this spin-spin correlation that you mentioned. There was a relatively old observation result by Hale et al.
1994?
That's one, yeah, okay.
Yes.
Okay, so basically they measured statistically the correlation between the spin of the binary system. And he found that if the separation is greater than 50 AU, then the two spin basically do not care about each other, whereas if they're closer than 50 AU, then they do care.
Right.
And
Yes.
that, I guess the current status, because that paper is very, very old, I'm wondering maybe you know this thing.
Can I follow up on
Yes,
that? So there's a
please.
recent paper by Justison and Albrecht from 2020 that showed that not that there is not evidence for a lack of alignment, but there is not evidence for alignment based on a statistical reanalysis of that sample. And also part of that was due to updated radii of the stars from Gaia. So as of right now, we can't say that observational claim is true. It doesn't mean it couldn't be. They didn't rule it out. They just say it's not clearly correct.
Well, that's certainly something for the near future, I think, where we could make new diagnostics and new
I'm always
progress.
very curious about this following question, namely, what is we all know, even outsider like me, the molecular cloud core, they are turbulent with this angular momentum coming in different directions. So there are certain coherence length scale. Is that 50? When I first learned about this 50 AU Hale result, I thought that basically reflect the coherence length of the turbulent region. Basically, everything within 50 AU, they're more or less rotated in the same direction. Therefore, everything. Right? We have the 50 AU is basically I was asking for the people expert. What do we know about from all this observation? What do we know about the coherence length in terms of direction of flows in the star forming region, because this may be whether they have any idea.
Well, I think observationally it's just a very poorly constrained because I mainly was this 1994 paper. So this maybe observationally not so robust.
But in terms of the molecular clouds, is that, but yeah, I mean, in terms of the on large scales in cores, there's not resolution to see if there is a length scale, the correlation length scale is 50 AU observationally. Right, because you're not resolving that. It looks like, did John have his hand up? John, maybe you can comment on this more, but typically, right, the observations of turbulence in molecular clouds looks as though, you know, it follows like the old Larson, like line with size relation, and it could be well explained by turbulence, but not on scales quite that small.
Yeah, so I forgot to lower my hand, but yeah, I would say I don't have anything to add other than, yeah, the turbulence seems to follow Larson's laws, but I don't think it's been really it hasn't really been constrained on that type of size scale. I think usually you once you run into a few hundred AU, you get into ordered motion due to in the disks or the rotating core, and it's much harder to see what turbulence is doing.
And just a quick follow-up on that, I mean, to point out another thing that maybe is useful to know about these clustered star formation simulations where you may observe more or less alignment is that different groups often use a different prescription for turbulent forcing in their molecular cloud simulations with a different exponent, you know, P goes like K to some power, and the choice of that exponent can impact the degree to which you get fragmentation on a given scale, and the degree of alignment. So in principle, if you could observe that better, it would be useful for constraining the underlying star formation models. But I think we're a little ways away from being able to do that.
Right. Maybe as last comment, maybe Nathan, and then Max can set up in the meantime.
Yeah, I just had a quick comment. I was just going to say, I agreed with the comment about comparing distributions of inclination distributions for inside and outside of clusters, based on some of the four-body simulations I've done just with point particles. When you make triples, there's no reason to expect an isotropic distribution of inclination angles between the inner and outer orbital plane, especially if you're angular momentum starved when you're making these things. And I don't know how subsequent interactions with any gaseous environment might affect that, but I think that's actually a very interesting question, and does bode hope for actually being able to disentangle dynamically formed versus in situ formed triples.
Okay, well, let's thank Stefan for leading this.